Hello everyone. So today we are going to solve for this RC circuit in which we have to plot the output voltage waveform and the current waveform for a pulse input, right, which has a duty cycle of 50% and it goes from 0 to 10 volts. So here we need to solve for two cases, right, for tau much greater than capital T, where tau is the time constant of the circuit and capital T is the time period of the signal, right, of the square wave, and for tau very less than T. So we will solve this in three methods. So first method is basically the steady state analysis. So how should we analyze this in steady state? So basically first we need to observe the circuit, right? Initially the cap was uncharged, it has zero voltage across it. So the circuit will look something like this at t is equal to 0 plus. V naught is 0 and basically this Vi, right, is equal to 10 volts and this R is whatever it is. So what is the current through this circuit? The current IC equals to 10 divided by R. This is basically the charging current, right? But what will happen is, as in our condition, the first condition where tau is much greater than T, so what will happen is it won't get enough time to reach steady state. By steady state I mean this whole voltage, right? It won't get enough time to reach to 10 volts, this cap. So it will charge to some value, then it will stop, because this waveform is stopping at t on, then it is going to 0. So first let us draw the waveform, right? So this voltage will charge to some value, let us assume this is like 2 volts, right? Then the voltage is going to 0. Now for that, after t on time, what will happen is the circuit will look something like this. This is C, this is R. Now this C has some 2 volts across it, and now what will happen is this 2 volts will try to discharge it. So what is the discharging current right now? The discharging current is 2 by R. Now as you see that this charging current was 10 by R and the discharging current was 2 by R, so it will discharge much slowly, but it will not go to totally 0, because this T here for the same condition is much less than tau, right? It will not settle to 0. So this will discharge to some value, let us say 1 volt, and then again an input will be applied at t is equals to capital T, right? So again here we have an input, but this time the cap won't be short circuit anymore. It has some voltage across it, which is 1 volt, right? So what will happen is the cap will have a 1 volt across it and there is an input of 10 volts, right? So what is the charging current right now? The charging current is basically 10 minus 1 divided by R, which is basically 9 divided by R. So as we can see, the charging current got reduced, right, from 10 by R to 9 by R. So it will get charged totally not to 2 like plus 2 volts, it will get charged something less than plus 2 volts, right? Because the charging current has reduced, but the time duration for which it is charged is remaining same. So it will get charged something to lesser than 2 volts, right? So this gap, this will be something less than 2 volts, like 1.5 volts. So where will this reach? This will reach around 2.5 volts, right? As the charging current is getting reduced, hence the the amount of voltage that it is being charged will also get reduced, right? That's why this is 1.5 volts. Now for calculating the steady state, we have to understand that the average voltage across this cap will be constant, right? Why? Because at steady state the cap will settle and the current through this will be 0, as the average voltage is constant. We know that IC of t is equal to C dVc of dt, right? This is the fundamental equation. So if the average voltage is getting constant, because what will happen is initially it is charging to 10 by R, now the charging current is reduced, but the discharging current will increase, right? It will increase to something like 3 by R, then 4 by R, and at a certain stage what will happen is this charging current, I charging, will be equal to I discharging, right? Then it will reach a steady state. Why? Because the average current will be 0. From 0 to t on, some charging current is flowing, then from T on to T some discharging current is flowing, and both of those cancel each other out and the average value becomes 0. Hence that will basically the steady state. So if IC average is 0, right, then drop across the resistor will also be 0, because IC average equals to IR average, as both of them are connected in series, right. Hence this whole voltage, right, of pulse input will come across this cap. Now as the drop across this is 0, so what is the KVL equation? V in equals to VR plus VC. Now if we take the average on both sides, right, so average of Vi is equals to average of VR plus average of Vc. Now as you have already established that this average value is 0, as IR average is 0, okay, 0 amps. So what is the average value of the input voltage? So the average value of the input voltage is equals to 10 into T by 2, as T on is half 1 by 2 plus 0 times T by 2 divided by T, which is equals to 5 volts, right. So this is the Vc average. So what will happen is, as there will be some charging and discharging current, it will not completely settle, there will be some ripple around the average DC value of the 5 volts, right. Then it will just charge and discharge around that steady state value of 5 volts, but it will never reach the 5 volt, it will just charge and discharge again and again. Let me plot the voltage waveform. Now what will happen is, this cap voltage will charge to some voltage above 5 volts, then again it will discharge below 5 volts, then again it will charge, and this will keep on happening. Now you might say, like, why is this linear, right, why is this not exponential? Because there was an RC circuit, right, this was an RC circuit. So in our case what is going on is, we are calculating e raised to power minus t by RC. For in our case, as the time period is really low and RC is really high, what is happening, this power is really small, so we can approximate this as e raised to power minus t by RC, right, and this is basically a linear function. So this is what is happening here. So this value is 5 volts here, and it will ripple around 5 volts only, the output voltage. Now what is the output current, right? So basically we know that the output current has a 0 DC value, right, so it will just go along this voltage. I of t is equals to Vi of t minus Vo divided by R during charging, right, and I of t is equals to minus Vo divided by during discharging. Basically this is the superposition. So during charging there is some constant 10 volts and this is some constant 5 volts, which is keeping on increasing. So the current will keep on decreasing, right, so it will keep on decreasing. Then what will happen is, suddenly T on, this current will happen, so it will go to negative, and as like V naught is decreasing, as it is discharging, the current will go down, then again it will go positive, then again it will go down, then again it will go negative, then it will go down. Like this the average current will be 0, and this value is 5 by R and this is minus 5 by R. Okay, so basically this is the voltage and current waveform for the first case, right, where the tau is much greater than the capital T, right, time period of the signal. Now next is this case where T is very greater than RC. This is very simpler case where the cap will have enough time to charge and discharge, right. So basically what will happen is, this is the circuit, this is R, this is C, this is the input waveform, right. So basically what is happening, that as T is much greater, hence T on will be also much greater than RC. So what is happening, it is getting enough time to charge. So at steady state what will happen, cap will basically get open circuit, R, and this is open circuit, and we have some applied voltage 10 volts. This will just see it as a step function 10 volts, hence the whole 10 volts will come across this. Then after T on, what will happen is this R and this 10 volts is there, and now this is discharging, right? Now this will totally discharge because it has enough time to discharge, as the time constant is much smaller than the time period of the signal, right? So what will the output look like? Basically the V of t will look like something this. It will charge to very fast, then it will discharge also very fast, then it will charge very fast, then it will discharge very fast, right? So this will get charged to voltage 10 volts. Why 10 volts? Because here the circuit time constant is much less than T on, right? As it is much less than T on, the circuit will reach steady state, right? So here it will reach 10 volt and remain at 10 volt for the whole T on period, and after T on this will get short circuited and this current will flow through here, and the voltage will go to 0 before the next cycle starts. Hence this will go to 0 much earlier than the next cycle starts, right? That's why the curve will look something like this. Now we have to calculate the current waveform. So the current waveform will look like something this. This is t, this is I naught of t. So initially what is happening is it is charging to a very fast value. So initially there will be some current, this is equal to 10 by R, then it is going to 0, 10 by R. Next negative current will happen, then it will also go to 0, this. Now why is this 10 by R, right? And this is why is this minus 10 by R. Now why is this current 10 by R and minus 10 by R? Let me just draw the circuit for you. So here we have some C and R. So at t equals to 0, right, what will happen? This cap will get short circuited, right, as it has 0 voltage. So we have applied a 10 volt across it at t equals to 0 plus. So this whole current will flow across this. So I C at t equals to 0 plus is equals to 10 by R, right? Now for steady state condition, right, steady state at t equals to T on, this cap has charged to 10 volts and this voltage source is gone. So here again we have one 10 volt source and this will discharge through this R in the opposite direction, right? In the opposite direction this will discharge, hence the current is same but the direction of the current is different, right, at t equals to T on. Hence the graph is looking something like this, and this is your understanding. It is settling very early to 0 volts, then again it is going to minus 10, then it is settling very early because the t is much larger than this, right, for the time constant. Now let us do the frequency domain analysis for this circuit. So here I have drawn the transfer function of this circuit, right? It is basically acting like a low pass filter, where the characteristics of a low pass filter is given here, and the cutoff frequency is 1 by RC. We know the cutoff frequency is the pole. So first we have to identify what type of signal are we giving, right? So at the input there is some square pulse, right? This. We know that for a symmetrical square pulse, the coefficient of the Fourier series is inversely proportional to the harmonic frequency, right? So the coefficient of the Fourier series, like a of 1, 2, 3 is something like this. It is basically 2 times this 10 divided by n pi. So this is basically the coefficient. Now as you can see, it is inversely proportional to n. How much more greater than the harmonic, the coefficient, the amplitude of the harmonics will get reduced, right? Now this is basically comes from a derivation of a square pulse. If you just put that in a Fourier series, then you solve for that, the result will come out like this. It will be inversely proportional to the harmonic frequency, right? Now in the case 1, right, where t is much less than RC, what will happen? So if t is much less than RC, so 1 by f is much less than RC, where f is much greater than 1 by RC, right? So basically the signal frequency is much greater than 1 by RC. So what does this mean? Basically 1 by RC is this, and the signal frequency will lie somewhere around this, right? And the harmonics will lie somewhere along this, so the gain will get attenuated even more. Basically only the DC signal will pass through this circuit, right? Because the DC signal has a frequency of 0, so this frequency will get passed with no attenuation, with unity gain, and other frequencies will not get passed. But one thing is for sure, the other harmonic frequencies will get passed with a very high attenuation, right? So it will have some DC component, but it will have a bit of ripple around it. So what should the output waveform look like? Basically, so this is the DC value, right? This is the 5 volts value, because the input DC will get passed to the output totally, right? So here V naught of average equals to 5 volts, as the average input voltage is 5 volts, as we have calculated earlier, right? So but there will be some ripples around this, right, as you have seen, the high frequency ripples. So the waveform will look something like this. It will just ripple around this 5 volts, right? But the average voltage will be 5 volts. Now from this we can easily find out the output current. Just solve for both two cases as we have solved this earlier, right? Basically the output current will be the same as we have obtained, right? So this will be 5 by R and minus 5 by R, right? Just basically solving the equations at 0 to t on, right? I of C equals to Vp minus Vo by R. I of C at t after t on, right, equals to minus Vo by R. So this is basically the waveform for I of t, right? Now let us solve for the other case where t is much greater than RC. So if t is much greater than RC, 1 by f is much greater than RC, or f is much less than 1 by RC, right? So if f is much lesser than 1 by RC, what is happening in the graph? So f lies somewhere here, right? F dash, f double dash or something. So it has minimum attenuation. It will almost follow the input, right? It has minimum attenuation for all the frequencies. 3f0, 5f0 will lie somewhere here, but much less than the cutoff frequency, right? So what is the input? Input is basically the square pulse, right? So input is basically the square wave. So what will happen is, this is the V naught of t. Now filter will almost follow the input, right? Will almost try to follow, right? But there will be some harmonics because there is some distortion here, right? It is not unity gain, there is some distortion, but the DC value will be totally passed. DC value will be 5 for this one, but it will try to follow the input. So the output will be something like this, right? So another method for solving this question is compression in time domain, right? How will this happen? So this will happen only when t is much less than RC, right? This method will work only when t is much less than RC. So for t much greater than RC, the calculation is much simpler, right? The cap will reach steady state and it again will discharge. So what were the outforms for t much greater than RC? And this was the VO, right? Charges very fast and discharges very fast. So this is basically the VO and this is the Vin, right? Now as you can see, like it's charging very fast and discharging very fast for t much greater than RC. Now like in our case, as t is much less than RC, it is not charging fully, right? It is not able to charge fully. Before charging, the voltage is getting 0, the voltage here is getting 0, again it starts discharging. So we are just compressing this, right? We are just compressing this waveform over one time period. If we just compress this waveform, how will it look like? It will look like something this, right? It's compressed, like this part is getting compressed, and this part is also getting compressed. It's not charging fully and discharging fully, right? It's something like this, and it has some DC value. Why it has some DC value? Because if I draw the circuit, right, at steady state, like we have already established this, that the cap will be open circuit, right? The current through this will be 0 amps, hence the whole average voltage will come across this, right? Like the average current across this is 0, as at steady state dvc by dt is 0, right? That's why, hence like this will settle to some DC value. So the DC value we can easily find out by this calculation. So this will be 5, and there will be some ripples. Now this is just for like intuition based approach, just to check like how the waveform will look like. This is just an like inspection. If you say like, if you compress this waveform, the waveform should look like something this. So if you are on a pinch and you want to calculate for this case, just calculate for this case, right? And then compress the value, just compress the waveform, then you will be able to get the idea of how the shape of the waveform looks like. So this is one method for solving this, right? But this is just an approximate method. Obviously you won't able to find like the exact values of this ripple, right? This is not happen, and you have to cross check with other methods also while using this method. This is just like based on fully intuition how the waveform will look like. So that's how the complete analysis of pulse waveform will look like for the RC circuit, simple RC circuit. I will also do post another videos for a CR circuit and other RL circuits also. So yeah, that's it. If this video helped in clearing your concepts, then please do like the video. Thank you.